Hey everybody, Dr. White back again. Today's a no-face day. I don't really have a good desk to sit at the moment of the making of this session. But I do want to talk about correlation coefficient in connection with bivariate distributions. So consider a bivariate distribution xy, okay? And we've talked about how you can get the expected value of the marginal random variables x and y. Let's do some shorthand notation for them. Expected value of x shall be called mu sub x. Expected value of y shall be called mu sub y. And how about the variance of x? Let's call it sigma squared x. And the variance of y, call it sigma squared y, just for short. Now, let us define a new quantity, the covariance of x and y. By definition, it is the expected value of the following function of x and y. X minus its expected value times y minus its expected value. Okay. In addition, the covariance divided by the product of the standard deviations of the two random variables shall be denoted by the Greek letter rho. That's not a P. There's like a little bit of a curve to it. It's the Greek letter rho, which is kind of their R, okay? Now, of course, this definition only holds good if the standard deviations are both non-zero numbers. They can't be negative, so they have to be positive numbers. Remember, it is possible for a variance to be zero if a random variable is a constant random variable. So we're just asking that they not be constant random variables. Anyway, there's a nice shortcut for computing the covariance, which I would like to go ahead and prove right now to make future computations easier. So say you want the covariance of x and y. Well, you could just go ahead and multiply out this stuff that you are taking the expected value of. So when you FOIL it out, you get this. And the expected value of sums and differences is sums and differences of expected values. In addition, like take this piece here, constant times random variable, the expected value shall be constant times expected value of random variable. So when you work that all through, you're down to this. Now, the expected value of y could be just written mu y for short, and similarly, the expected value of x could be written mu x for short. Now here, mu x, mu y is a constant random variable, so its expected value is mu x, mu y. So what we're really doing is taking away two products of mu x, mu y, and adding on one. And so the result is expected value of the product of x and y times the product of their expected values. Okay, so now that we got this shortcut, we need to really investigate, like, what does the covariance mean? To begin with, I'd like to point out what happens if two random variables are independent. This affects what their covariance would be. And the way we can check that is, let's look at the expected value of the product, which shows up in the shortcut formula for covariance. So it's the sum over the x's and y's in the sample space of possible value of the product times the chance that x and y attain those exact values. And because of the independence, the joint PMF is the product of the marginals. So think about this. You've got this little sum over the y's where, the x is fixed for the moment. And so the x and the f sub capital X of little x are constants as far as this sum sign is concerned. They factor out, if you like. And then the sum you've got left is just the sum of the PMF values for your marginal capital Y times Y itself. That's the very definition of the expected value of that marginal random variable. Okay, so now you've got this sum over x's, the sum of this stuff. But in that sum, expected value of y is just a number. So it can just factor right out of the sum. And then inside the sum of the x's, you are looking at the definition of the expected value of x. And I just like commutativity of multiplication here. So if x and y are independent, the expected value of the product is the product of the expected values. Now, covariance, the shortcut formula says covariance is the difference of those two. So if x and y are independent, the covariance is 0. You can kind of think of covariance as trying to measure how not independent x and y are. Because when they're independent, there's no difference between these two quantities. And maybe the bigger this difference is, the more dependent the two are on each other. That's sort of the idea. Now, it's not exactly that way, because although we do have that if x and y are independent, their covariance is 0, the converse is not true. There do exist bivariate distributions where the covariance is 0, but the two marginals are not independent. Example 423 in the book gives you such a one, so take a look at it. Okay, I'm going to throw up my own example of a bivariate distribution, and we'll just compute the covariance for it, just to get some practice. So here's my distribution. The sample space is these 9 points, where x can be any whole number from 1 to 3, and y can be any whole number from 1 to 3. So it's these 9 points, and I'm not marking the points with dots. Instead, I'm marking the value of the joint PMF. And if you look at these values, the 5 of them are 1/9 for a total of 5/9. And then if you look at the others, they're all over a 36, and they add up to 7 and 7, which is 14, 15, and 16. 16 over 36. Okay, and 5/9 would be 5 times 4 is 20 36. So if you add these all together, you do get 20 36 plus 16 over 36 makes a 1. So this is really a valid PMF. And you can compute, marginals in the usual way. And you can compute expected value of x and expected value of y in the usual way once you have the marginals. So for example, how about the expected value of x? Well, it would be the probability that x is 1 times the 1 plus some other stuff. What's the chance that x is 1? We'd have to add up the y's, the f of x y's that go with x is 1. And that's turn it all into 36s. 7 over 36, 4 over 36, 1 over 36. 7, 4, and 1 is 12. Okay, 12 over 36 times 1. And how about the next one? So 2 times the chance of 2, 3/9. Here's the chance. And similarly, if you do 3 times the chance of 3, you get another 12 over 36 times a 3. So actually, all these fractions are a third. So you're looking at a third of 1 plus 2 plus 3. That works out to exactly 2. So capital X, the marginal distribution is balanced perfectly around the 2, and the expected value came out to 2, like you would suspect. You'll notice a symmetry between x and y here in the PMF, so you don't really have to do the calculations, but if you did, you would find expected value of y is 2 as well. Okay, let's go for expected value of x times y. So we sum over the possible values of x, and then for each x, what are the possible values of y? Well, there's still 1, 2, and 3, so sum is easy to write. And so we do, xy times the chance. So we got to add up 9 things. And so you have to get the products. So like when x and y are both 1, the chance is 7/36, and you got to do 1 times 1, your x times y. Well, that's a 1. And then my next move is to do a 9th times the 1 times 2. Now a 9th is 4/36, and here's my 1 times 2. And I'm just proceeding that way. I'm going up the column, and then I'm going to go to the next column and go up it, and the next column and go up it. And I'm writing down the sums that I get. And I slaved my way through it and got 156/36. So the covariance, the covariance is that difference, 156/36 minus 2 times 2, which is 4. 4 turns out to be 144/36. So I get 12/36. The covariance is 1/3. Now, the exact value of that number is not so terribly interesting, but generally what you'll notice is that if it so happens that larger values of x tend to make larger values of y more likely, then the covariance will be positive. On the other hand, if larger values of x tend to make smaller values of y more likely, then the covariance is negative. So like when x comes out above what you expect, if you find that y would then come out above what you would ordinarily expect for y, not knowing what x is, then the covariance is positive. And same here for the other relationship. And so I'm getting a positive number here. So I'm kind of thinking that what might be happening is that if you find out that x is an above average number, then your guess at what y would be would probably shift up. And let's see if that makes sense here. Let's take a look at the PMF again. So like the average we know is 2 for x. What if somebody told you that x was 3, above average? Then what do you figure y might be? Well, there's only a 1 in 36 chance that it's a 1, a 4 in 36 chance that it's a 2, 7/36 chance that it is a 3. That's absolutely. But remember, if you've told that the x is a 3, then just focusing in on this, 1, 4, and 7, 1, 4, and 7/36, you can see that out of that, 7 is like more than half of the mass that's here. 7/36 is more than this put together. And so like your estimate of the chances that y is 3 is now like over 50% if you know that x is 3. Before you were told anything about x, your estimate for the chances of y to be 3 would actually just be a third. It's this added up. So so knowing that x was above average bumps up your estimate of like what y is liable to be. It's going to be like more likely to be 3 and less likely to be a 1. So there seems to be something to this, you know. So let's try now we've done a computation, let's try a sort of a more interesting problem. So remember the Bizarre Sorcerer from a couple of chapters back? Let's say he kidnaps you again, now that you know more probability theory, and he straps you to his shock machine again, okay? And he's got his little magic wand in his hand that can, you know, immediately conjure up trials of random variables. But this time, instead of working with a regular random variable, he's going to work with a bivariate distribution. Okay, and this is the distribution he's going to work with. It is the very same one that we've just done calculations with. And he shows you this distribution, okay? So like this is on a whiteboard somewhere and you're looking at it. And he says, here's what I'm going to do. I'm going to try out the distribution. So I'm going to get a value for x and a value for y. And I will tell you the value for x, but you've got to guess the value for y. And if you're wrong, I'm going to give you a shock. And I'll tell you the rules for how much shock you get in just a minute. And he's going to just like keep doing this all day, again and again and again. Shock, 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 shock. And of course, you don't want, your total shock to be too high. So he also imposes a restriction on your guessing strategies, okay? What you've got to do is you've got to draw a line with some slope b through the point of expected values of x and y. And so you know that that's the point 2, 2, okay? And so you're supposed to draw a line through that 0.22. And it can have any slope b that you like. So it can have like positive slope, like how I'm moving my mouse now, or it could have negative slope, like how I'm moving my mouse now, okay? You get to choose. But then you got to stick with it. For every x value that he gives the rest of the day, your guess at the y value has to be the y value that you get by plugging in the x value into the equation for that line. Okay? And now here's the rule on the shock he's going to give you. The amount of shock in volts is going to be the difference between the actual value of y and what you guess it is squared. Okay. So let's think a bit about the line that you get to choose. It's supposed to go through the point of expected values and have slope b. So what would be an equation for it? Well, if we let x, y be an arbitrary point on the line, the slope b could be expressed as y minus expected value of x over x minus, so y minus expected value of y over x minus expected value of x. Solving for y, that's an equation. So that, point slope form for a line. Okay. And, you want to minimize the expected value of the shock, right? Because you're going to get shocked all day. So you want to minimize the average amount you get shocked. So, what should we do here? Well, the expected value of the shock, following the sorcerer's rule, would be the actual value of y minus your guess squared. Okay, so the actual value is this random variable y, and your guess is the mu y plus the slope times the x minus mu x, and the x is a random variable too. It's going to keep changing all day. Okay, so you need to minimize that expected value. Now I'm going to rewrite the expected value just a tiny bit. I'm going to group the y and the mu y together, and then I have the minus I'm working through, and so I have a minus b times the this stuff. And then, of course, the whole thing is getting squared. Now, once you get the expected value, do all that summation, there's still going to be a b in your answer. So it's a function of b, and I'm going to call it k of b. And you want to find the value of b that minimizes k of b. Well, you can minimize function by taking the derivative, setting to 0, solving, finding the critical point, and all that kind of stuff. But in order to take the derivative of this function of b, you should probably rewrite it a little bit. So I've got this quantity that I've got to square. Let me go ahead and square it out. So we have the first term squared minus 2 times b times the product of those differences. That's our middle term. And then we have the second term squared, which gives us this b squared x minus mu x squared. And again, because the expected value is a linear operator, works through the sums and differences and the constants pull out, I have expected value of y minus mu y squared. That, by definition, is the variance of y. Now here I've got a constant 2b times the expected value of that product, but that, by definition, is the covariance. And then you can see here we're going to get the constant b squared times the variance of x. And I'm going to rewrite covariance using that definition of rho. By definition of rho, the covariance would be rho times the product of the standard deviations. So that's a much easier expression to take the derivative of with respect to b. And when I do it, the only stuff that's going to survive is stuff from this term and stuff from this term. And so I get minus 2 rho times the product of standard deviations plus 2b times the variance of the x. And set that to 0, solve for b, and lo and behold, b turns out to be the correlation coefficient times the ratio of the standard deviations of your two random variables, your y over your x. Now, is that a max or a min? Do the second derivative test. So if I grab the derivative of this, you'll see that I just am left with twice the variance of x, which is positive. So I have some concave up thing, and I must be at an absolute min. So the best line to use is the one whose slope is that. And so, that line, it may not cross any more than maybe that one point there, the point of the expected values. It may not cross any other points. And so most of the time you're going to get a shock, but it's going to basically, it's bending itself to try to be closer to points like this one here, that have bigger probability of occurring. You can tell that because the covariance, remember, worked out to be a third. And so the correlation coefficient is going to be a positive number. The slope for the best line is going to be positive, so you can see how it's bending towards this and this. So doing the best job it can to make sure that you less often get big shocks. So by the way, that best line actually has a name in probability theory and statistics. It's the least squares regression line. If you've been in an elementary stats class, you've actually seen it before. And that really is the correlation coefficient right there. The only difference between now and your elementary stats class is that in elementary stats, all of your points are assigned equal probability. All your data points have equal likelihood. And here you're in kind of a random variable situation instead of real data. Okay, that's enough, I think, for section 4.2. So I will see you another time.